Directional derivatives and the gradient, part 1. The directional derivative of a function at a point x naught, y naught has this notation down here. Like big D subscript u of f of x naught, y naught, where u is the direction that we're taking the derivative in, and very specifically, u is a unit vector. Now, you should have seen this right side expression, very similar for definitions of derivatives that we've been doing. And I'm not going to go through this necessarily, but what I want for us to do is understand it. So let's refer to this picture down here. I have a surface, z equals f of xy above the xy plane. There is a point in the xy plane, x naught, y naught. And of course a corresponding point z, or z naught, on the surface. Now, as I have explained, I like to think of my surface as a mountain. I'm standing on a mountain, and depending on the direction that I go, I would walk at a different slope. So what if I wanted to know the slope in a particular direction? Well, that's our directional derivative. But instead of saying I'm going east or whatever, I would say I'm going in the direction of a unit vector u, which we often write as a comma b. So if I was looking in that direction from that point, I would have a slope. And if I looked in a different direction, say something like that, I would be walking at a different slope. So we often use the theorem instead of the definition, as always when we're evaluating stuff. And without proof, just because the proof gets a little bit messy beyond the scope of the video that I want to do, we're just going to state the theorem and then we're going to use it. Suppose we have a directional derivative in the direction of a unit vector, AB. Then the directional derivative is given by the dot product of our vector of partials with the unit vector. And if we were to write that out, we would get partial of f with respect to x times a plus the partial of f with respect to y times b. Now, if u makes an angle theta with a positive x-axis in the xy plane, then we end up with u being the vector cosine theta, sine theta, and our directional derivative is partial of f with respect to x times cosine plus the partial of f with respect to y times the sine. Let's take a look at an example. Suppose that f of xy equals x cubed minus 3xy plus 4y squared. And u will be the unit vector in the direction theta equals pi over 6. Let's evaluate the directional derivative of f at the point 1, 2 in the direction of u. So let's start by finding our partials. Just a reminder, this is shorthand for kind of the full thing. That is, partial of f with respect to x is the partial of f with respect to x at the point x comma y. And we get 3x squared minus 3y. Then the partial of f with respect to y, which if I wanted to write it out fully, would give me partial of f with respect to y at xy, and that equals negative 3x plus 8y. Now, if theta equals pi over 6, then u is going to be the cosine of pi over 6, comma the sine of pi over 6, or the vector root 3 over 2, comma 1/2. Then our directional derivative of f at the point 1, 2, and to emphasize, this is the point xy equals 1, 2, is going to equal the partial of f with respect to x times my a value plus the partial of f with respect to y times my b value. And both of these are at the point xy equals 1, 2. So now I can plug in 1 for x and 2 for y. I get 3 times 1 squared minus 3 times 2, and then times the root 3 over 2. So I plugged in the 1 for x and then the 2 for y. I'll do the same thing for the partial with respect to y. I get negative 3 times 1 plus 8 times 2, and then times 1/2. And once again, I plugged in the 1 for x here, and then the 2 for y here, into the partial of f with respect to y. And simplifying this out, I would get negative 3 root 3 over 2 plus 13 over 2. Quick definition. The gradient vector has this notation right here. Looks like an upside down triangle of f of xy. And very specifically, the gradient vector is the vector of the partial derivatives of x and y. And if I had another dimension, it'd be then comma f with respect to z. So let u be the unit vector, AB. Then, as we can see from how we define the directional derivative above, the directional derivative of f at xy in the direction u is the gradient of f dot u. Pretty straightforward. Let's take a look at one example here. Suppose that f of xy equals x squared y cubed minus 4y. And we want to find the directional derivative. I'll give it different, I'll call it v, of f at the point, say, 2, negative 1. Where v is going to be the vector 3, 4. Now, do you see an issue with this already? When I want to find the directional derivative, I really should have put the directional derivative in the direction of u, where u has to be a unit vector. That is, u has to be a vector with a magnitude of 1. Well, if I'm in the direction v, I know that u would be v over the magnitude of v. This is how we find a unit vector in the direction of a different vector, which is going to be 3, 4, and then the magnitude of v is 5. Right, it's going to be the square root of 3 squared plus 4 squared. But I already knew a 3, 4, 5 triangle, so I knew it was going to be 5. So, let's find this. We're going to start by finding our gradient. I'll put the gradient of f equals, actually let me give myself a little more space and write it well. We're going to have the gradient of f equals the matrix. Sorry, well, it's a matrix, but the vector f of x comma fy, which is going to be the vector 2xy cubed That's the partial with respect to x. And then the partial with respect to y is going to be 3x squared y squared minus 4. And then our directional derivative in the direction of u of f at 2, -1 would be the following. It would be 2x y cubed, comma 3x squared y squared minus 4 at the point 2, -1, dotted with my unit vector 3/5, comma 4/5. And plugging in values, let's plug in 2 for x, so I'm going to get 2 times 2 times -1 cubed. Plugging in for the partial with respect to y, we get 3 times 2 squared times -1 squared minus 4. And then dot our unit vector. So we get -4, comma 8, dot product with 3/5, 4/5, and that's going to give us -12 over 5 plus 32 over 5, which is 20 over 5 or 4.